Now that I have the board assembled, it's time to wire it up. And we'll try to start in the same way that I have the lecture slides, which is focusing on the battery and its connections, and then working our way to the the motor driver and connecting it over to the microcontroller. And then finally we'll connect both motors. And the motors will connect to both the motor driver, not surprisingly, since it'll have to control the power to these. But the motors, the connector heads on those, also get connected to the microcontroller so that the microcontroller can read the speed of each of the motors. Alright, let's start over here with the battery connectors. There are 3 wires coming off the ground side of the battery and 2 wires coming off the positive side of the battery. Flipping our prototype over here, you can see all 3 wires coming off of the ground side. One of those wires goes directly to the motor driver, one of the wires goes directly to the voltage tester, and one of the wires goes directly to the expansion board. So flipping this over on the other side, let's trace through where those 3 wires are going. Here's the wire that should go to the, this is called a DuPont connector. This should be plugged into the motor driver. This wire I'm not going to tug on too hard is going directly to the volt tester. And I already plugged in the battery connector, so that's already connected into the expansion board here on the side, which means the positive wire is also already connected into the expansion board. That connector is one piece. So I pushed those out through the bottom and connected them directly into the expansion board. Those are directly connected because I can flip this switch on the side of the expansion board to turn power off and on to the microcontroller on the expansion board. So I always have the ability to turn off power to both the the control systems and to the motors themselves, and those are on 2 separate switches. I've got my switch here on the side that controls power to the volt tester and the motor driver, and then a switch here for the microcontroller. Looking at the diagram, out of the ground connections coming out, this one's already complete, the one going into the volt tester, and this one's already complete, going into the expansion board. So the last one is to trace this wire here into the upper corner here of the motor driver. The things you should key on from this diagram, in the image, this is pretty common, is the pin here is square to denote that it's the ground pin. Same thing on this side. Both of those are actually connected to each other, and they're both connected to ground. So I'm going to connect the battery pin to that square pin here on the board. So let me find that male header, DuPont connector rather. Here's the connector. It's going to go directly here into the corner. Likewise, the red connector, which is connected to the battery, gets connected directly next to it. I encourage you to trace both of those through this diagram. It's hard to see through the video here, but the 2 wires end up directly connected to the motor driver, right next to each other. So that's all of the power connectors. We basically have 3 contacts that the battery connects to. The expansion board, both sides are connected. The motor driver, both sides are connected. And the volt tester, both sides are now connected. Now we'll move on to connecting the microcontroller. The microcontroller is conveniently arrayed so that all 6 pins here connect in order to all 6 pins on this side. So I just need to find enough jumper cables, to connect all of those together. And I try to stay consistent with my wire colors. So I will start with the ground connector with a black wire. Here's my black wire. And looking at the diagram, if I'm looking at the end with the USB connector, I know that the ground pin is 1 in from the edge. And these shouldn't need too much force to go down into them. and that goes directly into the ground pin of the motor driver. I'm not impressed with that cheap jumper cable. The next in line is the 3.3 voltage for logic, and it goes directly next to that same pin in the breadboard. And don't forget, the breadboard, all receptacles in a row are connected to one another. So even though those are spaced fairly far away, the black and red wires there are connected to the motor driver. Something that's probably not very apparent from just looking at the diagram is this connection here. It goes from VCC on the motor driver down to mode on the motor driver. The motor driver has two different modes of operation. One is called the phase enable mode, which is the mode that we will be using. And the way that you enable the phase enable mode is by setting the mode pin to high. You have two ways to do that. We could use one of the pins on our microcontroller, but there are precious few GPIO pins, and I don't want to waste one of these GPIO pins just to always set this mode pin to high. Another way to set it to high is just to wire it directly to VCC. So I have a wire going directly from VCC to the mode pin so that it's always set to high. Plugging into VCC and then directly over to that mode pin. This will now always be in phase enable mode. Next is to just plug all of these wires in order. And that was a deliberate decision that I made when laying out the schematic. This distance here is just about perfect to not put too much pressure on these wires. It's not too much of a stretch on this white wire. And now the wire's mostly out of the way. I'd recommend not worrying about having the wires too much look like too much like spaghetti wiring. It's alright if they bridge too high and it gets a little bit hard to keep track of all them. That's why you're sort of doing code reviews in terms of your wiring. Everybody will be required to have a TA look at their wires and two other groups look at their wiring before they're given batteries. That also spreads the blame a little bit if something goes wrong. It's not just on you, it's on me and the TAs to ensure that every wire looks like it's connected properly. With the cover on my expansion board, it's a little bit difficult to get that last one in sometimes. Alright, I am now able to control the motor driver. I can send speed signals over two of the wires and direction signals over the other two wires, so that both motors know which direction to spin to make this thing go forward or backwards, or to rotate in place if I put them in opposite directions. The last connections to make are for the motors themselves. So motors each have power coming into them to actually turn the motor. That's pins M1 and M2. And since these motors are put onto the board as mirror images of each other, I'm actually going to flip those. So looking at the motor driver, I have pins called B out 2, B out 1, A out 2, and A out 1. In my diagram here, A out 1 is connected to M2, and B out 1 is connected to M1. So those will be sort of flipped, so that both of them I can say direction is 1 and reverse is 0. There are two different ways to reverse the direction of a motor. You can do that in software by changing the direction, or you can do it in hardware by changing the direction through the direction of current flowing through the motors. I've chosen to do that in hardware just because it makes the software easier to read later on. So let me get those plugged in. Let's see. Let me face this the correct way. This is my left motor, and it looks like I have my left motor in the diagram being connected to the pins closest to ground. And it goes red, white, white, red. Those are both plugged in. And now I will plug in both of the right motor's power pins. The last pin on the motor driver is actually not connected to anything. It just is not functionally useful for our diagram, and it doesn't need anything special. No special care needs to be taken for it. The last pins are all of these other pins coming off of the motors, and these are used to read the speed of the motor. So looking at the diagram, the green wires are C1, the yellow wires are C2, the blue wires are ground, which is obnoxious, those are normally black, and the power wires are black, so the opposite of what they would normally be. So I'll start with the confusing wire, the black wire coming off of both of these. Those need to be wired to power. And one way to wire them to power is to just put them in the same row as the power pin connecting to the logic side of the motor driver. So that is where I will put both of those black wires. And it will be almost impossible for you to see in the video. That's something I would be happy to help with in person. Alright, what color are the ground pins? Those are the blue pins. And the blue pins need to go next to the black pin on the logic side, actually either side, of the motor driver. I'll stay consistent and put them on the logic side, since this is a logic circuit that's being powered. But as I said, all grounds will be connected together. The battery ground and the logic grounds will be connected. The power sides will not be connected. Those will be isolated from one another. Alright, finally we have the pins that actually read out the speed of the motor using what's called a quadrature. So GPIO 1 looks like it should be the green pin from the right motor. Green pin, right motor. GPIO pin 1. The second pin from the right motor, the yellow pin, goes into GPIO 2 right next to it. These also were just chosen in software, but if you stick with the pins that I've done, you can also stick with the code that I will write. GPIO 3 is connected to the green pin of the left motor. So third one in a row. And unfortunately, I couldn't make quite the sensible decision, as sensible a decision for the last pin. GPIO 4, which is the next place that might make the most sense for the final pin, is also the pin used to control the speaker. So it turns out, when I first tried that pin, when I was controlling the motor, I'd also hear little chirps from the speaker. I could cut the signal to the speaker, but it's kind of nice to be able to have the speaker, so I jumped it all the way down to pin 43 here at the bottom. I want to avoid using the next two pins. Those are actually digital pins 5 and 6, because those will be used for communication with other peripherals. So for example, the OLED display here on the back uses those two pins. And so will our initial measurement unit and our LiDAR, which we'll use later on in the semester. So final, yellow pin goes to GPIO 43. I regret buying such cheap jumper cables. Luckily, once we get them in once, they shouldn't need to be rearranged pretty much ever.